Hello. I was approached yesterday by someone asking what you might use for a low-pass filter if you had a microcontroller. And I realized that it might be good to go over this filter here. This is a single-pole low-pass filter, and it is probably the most common filter ever used. Probably used 90% of the time you ever see a filter. And it's sometimes called a single-pole smoothing filter or a smoothing filter. And the idea is you just take your input, you multiply it by some fixed value, 1 minus alpha, which typically might be something like 0.1. You add that to alpha times your previous value. By the way, if you're really concerned about computational efficiency, you could have alpha is equal to something like 15/16. And then 1 minus alpha is equal to 1/16. And so when your input sample comes in, you shift it right by 4 to divide it by 16. And alpha times y is equal to y minus y shifted right by 4. And so you have no multiplications. Can be done very, very efficiently. So our transfer function looks like this. Alpha is going to be real, and as noted up here, alpha is usually close to 1. So how do we analyze this? What's the frequency response? Well, the easiest way to go about a frequency response is often, if we're going to do it analytically, is to look at the frequency response squared, because it gets rid of the imaginary parts. It makes life a little bit easier. Magnitude squared, not just squared. So we take h of z evaluated at e to the j omega and multiply that by its conjugate, come through, and we get this box term here in green. Okay, I admit that actually doesn't look much simpler than what we had before, but at least we have something that we can analyze. So the first thing we're going to do when we analyze something like this is let's find out what its DC gain is. In other words, when we put in omega equals 0, what do we get out? Well, that's nice. We get out a value of 1. So DC gain is 1. As a low-pass filter, that means that the low frequency gain is likely near 1, which is what we would want. And I made these notes ahead of time while watching a show last night, so you don't get to see me them unfold as I develop them, which is a advantage and a disadvantage. We get to go through it really quickly, but it's also a lot of information at once. So the next question is, what is the cutoff frequency? Well, when we talked about cutoff frequency when we did filter design some time ago, and we found that we had this kind of idea of a pass band kind of band and a stop band, and the cutoff frequency was right there. Since we're approaching this the other way around, we already have a filter and we want to know what the cutoff frequency is, the standard is to actually just say, well, where does the magnitude squared equal 1/2? That would be our cutoff frequency. So we're going to try to find omega c where the magnitude squared of the filter is equal to 1/2. This is a little bit different than what we did before, but it's very common in analysis of filters of this type. So a little bit of algebra, multiplying things out, setting that equal to 1/2 right here. We cross multiply and get the omega on one side and everything else on the other side, giving us that cosine omega is equal to this quantity. Well, it's hard to get anything past here in terms of theoretical work. At this point, we want to just stick in numbers. So, over on the right, I've got a table that put together with a few values. When alpha, I like to relate things back to real frequencies. It's a lot more intuitive than saying, oh, 0.72 radians. People, oh, 0.72 radians says, yeah, what is that? It's kind of like giving the temperature in Celsius to somebody who only knows Fahrenheit. So what I've done is related each of these alpha values to a cutoff frequency that would be experienced if we were operating on a signal that was sampled at 8 kilohertz. 8 kilohertz is commonly used for speech. Now 16 is a little bit more common, but this gives you some idea. So if we had 0.5, we get a cutoff frequency of 920. Since the highest frequency we could expect would be 4,000, this is about a quarter band cutoff. It's not a very sharp cutoff, but it's about a quarter band cutoff. That's where the cutoff frequency is. Typically, I see these used down here in the 0.9s. So for example, if we do 0.97, we have a 39 hertz cutoff. If you want it to be really, really tight, 0.995 will get you a 6 hertz cutoff. So over here on the left, we have a plot. It's the same thing. We're just plotting the magnitude of this frequency response. The top plot is on a linear scale, and the bottom plot is on a dB scale. So this is for 0.9, and that's where we would have a cutoff of 134 hertz, or it's pretty small. It just comes down here. One of the things you'll see is it's even way out here. It's not real close to zero. If you wanted something that was closer to zero, you would have to throw some zeros in, which complicates your filter just a little bit, but wouldn't be hard to do. On the dB scale, you can see that it initially drops off at a reasonable rate, and then it flattens out. And the best you get is about minus 25 dB of attenuation. So not the best filter, but it's really easy to implement. And so it's very commonly used as you have values coming in and you just want to smooth them out. This should be your go-to filter.